Thanks for joining us for this new session of the Victor short course. So today what we want to talk about with you is what we call model benchmarking or model validation. So basically, we want to give you first like a state of the art of what's been done so far on comparing models from various volcanic processes. And then we want to show you an example of one of the code that we have on, well, actually two notebooks. One notebook about lava flow benchmarking, so comparing lava flow models. And then another one is going to be one of the code that we have available on Victor for validating models, or at least assessing the performance of numerical models in volcanology in a quantitative way with a model that is called BAM for best fit assessment of models. So we're going to do that in two parts. I'm going to start with an overview of what's been done so far in volcanology in modern benchmarking. So I'm going to share my screen here. All right. Okay, so just a brief overview of the state of model benchmarking in volcano science. And so I'm going to start with why do we want to compare models? So going back to a report from the National Academy of Science in 2017 that stated that a common theme in many of the questions and priorities is the importance of developing models to interpret the new generation of high-resolution observation and to enhance understanding of magmatic and volcanic processes. So in this report, they actually highlight that community-wide model intercomparison and validation exercises can lead to important advances and also highlight deficiencies that need to be addressed by future research. Equally useful is validating models with controlled laboratory experiments and well-constrained field data sets. And then they finally said that such exercises are particularly valuable when they are combined with the suites of data from laboratory experiments, observation of the geologic record, and targeted real-world case studies. So what are we looking at when we do some model comparison? We're looking at the sources of errors and uncertainties that can arise from numerical models. And there's two main types, as you may know. So one is called aleatory uncertainty. There's actually a natural variability of, for example, volcanic flows or tephra fallout or volcanic plumes, for example, or lava flows. And this is pretty hard to assess or to even harder to reduce, right? Because it really comes from the natural phenomena that is in play here or that you want to simulate. The second one is the one that you really want to target and try to reduce. It's called epistemic uncertainty. And it comes from any estimation of input or output parameters from your model, or it could also come from the mechanical or physical understanding of the volcanic processes. For example, what is the rheology that you want to use for lava flows compared to pyroclastic density currents, for example. And this is really something that you want to target and you want to highlight when you do such intercomparisons of models. So there's several ways of trying to address these sources of uncertainties. And here I highlight three main ways of doing that. One is called model validation. The other one is called model confirmation or calibration. And the other one is called model benchmarking. So starting with validation, validation is actually a process of trying to find out to which degree a model is actually an accurate representation of what you want to simulate. And so this is generally done from the perspective uses of the model. So it's generally made by the user and it's actually starting from some ground truth data. So it can come from, for example, a map deposit that you have from a lava flow, from some tephra fallout or pyroclastic density currents, and then you want to try to reproduce these deposits or this flow outline, right? In terms of the runout, but also the spreading. So you want to reproduce a footprint of that process that occurred in the past at a particular volcano. So if you want to do that, then you can try to do some numerical simulation using a model, and then you can try to compare the footprint that you get from your model to the actual footprint from the field data or from a laboratory experiment. So that's what is called validation. Confirmation calibration is quite the same, but is more like a best fit approach where you're going to do like a trial and error, trying to match the distribution of dependent data in a numerical model with some observational data. So it's a level that is a little bit less than the validation in the way that you can have several solutions to a particular problem, and it only supports the probability of the veracity of a model. And yeah, always more than one theory can actually explain the available observation. And then finally, benchmarking is where you're going to compare different models. So the two first are mostly like single model approach, but then the benchmarking one is really a comparison of models that aim at simulating the same physical process upon common initial and boundary conditions and outputs as well. So it's really important that when you want to compare a model, you're actually using the same source condition. And that's tricky because some models are actually asking you different inputs, right? And so you want to try your best to, even if there's differences between the kind of input that each model is asking you, you want to try the best to actually use the same comparative values. So then you're really using the same initial and boundary conditions. So then you can really compare the outputs of each of the model. And so each of these models are going to use different numerical approximations and techniques, like we've seen in the past sessions that we've done in that course. Like there's different ways of representing, for example, tephra in the atmosphere, or a lava flow or pyroclastic density currents by using either like a single phase approach where you're going to assume that the particles and the gas or everything is mixed into a continuum in a single phase, or if you want to discretize that by separating your solid particles from your gas, or for example for lava flow having like crystals, bubbles, and that is basically intricate to each of the model, right? And so you're gonna have to deal with these differences anyway. So that's why you really want to get these initial and boundary conditions to be the same. All right, I'm going to go through a few previous efforts that have been done for different types of models. And I'm going to start about 20 years ago because that's basically where this whole benchmarking initiatives started. And one of the first one was conduit flow model. So remember last week we talked about the Comfort 15 model. That is one of these conduit flow models. And so there was a workshop in Durham, New Hampshire in November 2022. Actually, it started and then they did another one in 25 to compare about 20 models from one-dimensional cylindrical conduit models to three-dimensional multi-phase models. And the scenario started with host magma that was containing some bubbles and ending at the vent, or the point at which the ascent rate reached the speed of sound in the magma, whichever comes first. Remember that the same conditions that we had in the Comfort model. And they came out by comparing these models and then some list on the right side of needs, either for experimental needs or optional needs based on the results of the benchmarking. So what they basically say is there is a need for development of transient multidimensional approaches to account for example, the complex dynamics of magma ascent or the interaction between the magma and the conduit walls that is ignored by most of the models. So that was the first really workshop that came out with some recommendations for improving models in volcanology. Then the Tephra Fallout community followed up quickly and did a first workshop actually two workshops in Geneva in 2010 and 2013, and then some paper came out of this where they tried to compare about 12 volcanic ash transport and deposition models with various approaches, numerical approaches. Some of them were more analytical, some of them more numerical, and some of them were using Lagrangian versus Eulerian approaches, which are just different ways of solving the partial differential equations, especially for advection and diffusion. And so you can see the table on the left here is showing you some different scenarios. So they had like a weak plume scenario and then a strong plume scenario. And they use different models, and for each of the a couple of models, a pair of models, they were ended up with some a difference index from 0 to 1, and you can see that the smaller this different index is, the better it means that the match between the outputs of the two models. So you can see that for some input parameters and output parameters, and the differences were pretty big, and for some others it was pretty low, and it really depends on the type of model as well. If you compare a 2D model from a 3D model, then you're gonna have more differences there. So they found out is that some of these discrepancies are probably due to the use of different physics, different parameterization of the source term, and slightly different input choices. So they ended up with listing about 15 recommendations for future model improvement. Then the Plume community came up and said, okay, we're also going to do our benchmarking exercise, community-wide benchmarking exercise. So in 2015, I think, they actually did an international workshop where they had 13 different Plume models, and they were running one-dimensional to three-dimensional numerical simulation using the same volcanic and meteorological conditions. And they also had like a strong plume, weak plume scenario, and you can see on the right side here some of these scenario using 4 different models. And they were looking here, I think, at the particle concentration and the entrainment of air in the plume. And the key differences that they found out between the models are how you treat the gas particle mixture, the water microphysics, the turbulence in the plume, and then the numerical discretization and solution methods that are different from one model to the other. In terms of 3D model output, they say that the key difference is the threshold between buoyant and collapsing regimes. So at which point you're going to get the plume that's going to collapse on itself to produce paraclastic density currents. And they also emphasize on the strong control of the entrainment processes on plume dynamics. As you know, air entrainment is a big deal, and so for some models that actually don't take that into account or simplify the terms for air entrainment, that's where some differences were noted. So they came out with some needs, especially to more accurately quantify entrainment rates, improve the representation of the plume radius, and incorporate the effect of column instability in future one-dimensional plume models. Okay, in the same time, there was some communities a little bit outside of volcanology, especially in the granular flow / landslide / debris flow communities that started their own workshops. So it started in 2007, and they did another one in 2018, where they compare some 2D and 3D mass flow models using various numerical approaches again. So Lagrangian or Eulerian hybrid, smooth particle hydrodynamics, and then discrete element modeling. And they were also using different rheologies. So they had 6 benchmark cases divided in groups, one for rock avalanche, mud flow, debris flow, and some like prediction cases for forecast. And they were comparing the output of the model with some past events, so using mostly validation there. But because they had different models, they could also do benchmarking. So what they found out is that similar output were obtained from models with different numerical solution methods, but using the same rheologies, which seems that for these types of models, the rheology is really the key, more than the way you're gonna formulate your equations and solve your equations for the transport and the deposition of the landslide of the debris flows. And they also found out that there was a lot of discrepancies due to assumption about internal stresses based on the Savage-Hurler theory, and also whether it assumed a mode of entrainment and basal erosion. And so internal stresses are pretty important in these models because they're gonna control how the flow, the model flow, is gonna interact with the topography, especially if you have different channel geometries, or if you have some obstacles and things like that. So we call these curvature terms, and these curvature terms are really they are like stress tensors, and they're really important in these kind of processes to actually get a better match with observed data or laboratory experiments. All right, and then the lava flow community came up in 2015 with some benchmarking. And so 2 papers came out of this. And what they did is that they used mostly experimental data as benchmark, and I think 1 or 2 real case study. And they look at the accuracy and the speed of several lava flow modeling codes, 2-dimensional, 3-dimensional, and so they look at some of the cellular automata model. Remember, we talked about one of these that was called Molasses, that is available on Victor. That is mostly doesn't have any physics, right? But it's just using the digital elevation model and the elevation difference between the different cells to spread an initial volume of lava. So they had 5 benchmark cases simulating different types of flow, viscous, cooling, and solidifying flow over either a horizontal plane or a sloping surface and into topographic obstacles. And what they found out is that the models accurately simulate viscous flows with some variability in flow thickness, where the flow intersects obstacles. So I ended up with some profiles here, like as you can see in A and B, of, for example, run-out distance with time, where they compare an experiment with different codes. And then they add also here the flow thickness against time, comparing some experiments with different codes. And then in the end, they ended up with this table here that is looking at the root mean square error between models, so basically discrepancies between models, and some case studies or benchmark case, right? So you can see here, the higher the number, the more differences there are between the model output and the case study. So they ended up with some recommendation about the fact that lava flow models could be refined by including benchmarks and employ multi-phase material like bubbles and crystals, for example, crystal growth, and also changing effusion rate at the vent. So I think Sam is going to show you a notebook next about some of this lava flow case study, benchmark case study that you guys can run on Victor. Moving into paracastic density currents, I'm going to have a few more slides here because that's what I'm mostly interested in my research. So it started late. We're always late in the PDC community compared to other communities, but in 2015-16, we started to express the need for community-wide efforts. So there was a few large-scale experiments that started at that time, and one of the first one is the Pele experiments in New Zealand from Gert Luber and others. That is a pretty large fume of about 20 meters long that is actually releasing some material from a hopper at a particular height, and then let some mixture of gas and particles to flow down a fume where they could put a lot of sensors in there, about 200 sensors to record time series data of flow kinematics and geometry, deposition, vertical stratification of the velocity, concentration, temperature, and particle size distribution. So really, the first time we were collecting such various quantitative data that then can be compared with some numerical modeling. So they first did some comparison with 3D multi-phase codes to examine the coupling between the turbulent and the non-turbulent region of the flow and the flux of material across this domain. So we did a first workshop in New Zealand in January 2019 to talk about the differences we were observing between some models and the experimental data and how we could close that gap. And here you can see one of the outputs that was used at that time is integrated flow height and velocity with time. So it's like a cross profile of the experimental flow, but integrated over the different time where the flow was propagating in the flume. So that can be used to compare velocities and flow height you get from a model inside the same digital representation of that large fume apparatus. So at USF, we also started doing similar things. So I had a postdoc, Valentin Guignot, that started to work on some synthetic topographies based on common topographic features mentioned to cause PDC to overspill. So we were more interested in how a channelized flow can actually leave the channel to spread on the interfluve. And so what we did is we created 4 different synthetic topographies, 4 different channel geometries, one with a bend, one with a break-in slope, one with an obstacle in the middle, and one with a constriction in the channel, so reduction in the channel width. And we also had like a flat incline as a control case. And after creating this digital topography, what we did, we ran some models. So we look at 4 different models, Titan 2D, Voltflow, Charlotop, and IMX. And we compare the propagation of these models into the synthetic topography in terms of thickness evolution and a center of mass velocity. And then we look finally at the final footprint of different case studies. So we varied the mass flux. So we had a low mass flux case, medium mass flux case, and high mass flux case here from red to blue. And as you can see, most of the model was showing us a few discrepancies, but mostly small discrepancies, except Titan, where we realized that there was a problem with how we use the flux option in Titan. So that's also the good thing, right, with this type of benchmarking, is that you can actually identify either some errors based on like how you use the model as a user, or you can also identify bug in the code. So as a code developer, it's also very important to actually either yourself run the code or put the code available for such benchmarking exercises, because what happened in Titan is that we had first an error in the flux parameters, but also the developers found out that they had actually not very accurately implemented the rheology that we use, the Volmi rheology, in their code. So they send us a corrected version, and then boom, finally, this is what we got after the code was corrected. So much better fit with the other models. So this kind of benchmarking is because you don't have a true solution, right? We don't have a solution to compare to. It's not really a validation, right? It's just like a comparison of an evaluation of the differences between the models. And so it's a bit different from the other benchmarking approaches that we've seen, where you have an exact solution and you're looking at how your model is fitting that exact solution. What we did also is to build a new large-scale apparatus at USF. So you have a picture here of that apparatus in cross-section here, where we actually cut a channel, and we try to reproduce some of these synthetic topographies that we build on the computer, but then having it as an experiment. So for example, here you can recognize a bend case with a 45-degree bend. And what we did is that we tried to look at the condition for the flow to actually leave the channel at the bend location here. And you can see that some of these flows did. And so for that, we were not using natural material, we were using glass beads that we put in a reservoir, and we fluidize these glass beads until they reach full fluidization, and then we release this mixture as a dam break condition. So you can see some like screenshots of what happened when the mixture of glass beads and air are hitting the outside of the bend. We first have a front splash here with a rollback wave, and then finally there's a second wave that is coming, creating a granular shock, and then it's going to actually create that overbang front that we see also in natural cases. So it was pretty interesting to see that at first, when the flow hit the wall of the bend, it didn't create the overbang first. We really needed a second wave to do that. So in order to get that overbang flow, we needed to increase the slope of the channel. So we did a lot of different experiments, and these are just here highlighted. And what we found out is that when we increase the slope from 3 degrees to 15 degrees, we're starting to develop some instabilities in the mixture through the form of the development of a second front wave here that you see that only happen at like 12 degrees and 15 degrees, so the red and black curves of the slope. We don't have that second wave coming for if the slope is lower than 9 degrees. So which means that because that second wave is really the one that's gonna produce that overbank, what we found out is that you need a minimum slope angle to actually create that overbank, and that was nice to actually being able to quantify that. So these are the summaries of what we found out in that paper from 2022. So the slope angle is actually controlling the flow discharge rate, causing the super elevation and the overspill out of the channel. The fact that high channel slope angle and discharge rate favor the development of discrete internal flow pulses, we've seen here. And then that there is a positive correlation between the runout and the channelized flows, and that overbank deposits actually oh, I don't have the end, but actually the runout of the generalized flow and the overband deposit are actually positively correlated. So finally, some next step. There was a paper published in 2020 from Espostion-Garot et al. That actually proposed a new example of how to classify the different benchmark cases in terms of their complexity. And I think this has been also done for other volcanic process. So, for example, starting from a unit problem where you're only looking at a few variables and you simplify your problem to the much that you can. So, for example, you're using a flat plane and you're just looking at the propagation of an incompressible turbulent gravity current on the flat plane. And then you can increase the complexity going from the unit problem, so the tier 3 here to the tier 1 and 0, by including more variables to look at. For example, you move from a flat plane to an inclined plane, and then you put some stratified currents in there, etc., etc. So comparing numerical solution with experimental and observation, as I said, at different level of complexity. And so different modeling approach and approximation can be adopted to deal with the large epistemic uncertainty of the natural system. So the way is to, get for each of these validation tier to actually get a suite of cases and models to actually compare, to actually move up into that pyramid here to reach the complete system where you can have a plume that then collapse and then produce progressive density currents, for example. So having also some kind of like cascading hazards inside your benchmarking cases. And so finally, the best way to actually do that, this benchmarking exercise, is actually to use cyber infrastructure like Victor, right? Because you can actually integrate all the inputs, the different models, the data set as well. You can actually go and pick up the data set that you need all into one common place. So that could really facilitate this kind of like intercomparison of data and models in a open, transparent, and inclusive way. So I'm going to stop here. I don't know if there's any questions so far. I think maybe Sam, you can maybe start showing the notebook for our lava flow benchmarking.
Sure.
And then I can, and then I can come back to explain quickly BAM, and then we can then show the notebook for BAM.
Mm-hmm. Sure. All right. Can you see it?
Yep.
All right. Great.
So I can answer the question on the chat while you're doing that. Thanks.
Okay. Sure. So what I'm gonna do right now is just more of a brief run through. But you can, if you're interested, we have a Victor benchmark command. So currently it's these two. The PDC one is not quite as far along as the lava one. We're working on finishing up a paper for the lava benchmark. But you can press 1, press 2, and it will generate everything you need. So if you want to just follow along through the notebooks, you can, but you probably won't be able to run them in time, especially because of some of the other models. So just for example, so we have the just like a point source on a flat plane. Yeah, you can see right here, we have kind of give a brief overview of this background where it's a hot Newtonian fluid. Anyway, how it works and how we try to make it work for all of you is that basically all you all you have to change is one value, and that's the volume, and you can choose not to. We have it defaulted to the actual like experiments, and then the analytical equations derived from those. But really all we have is just some notes, but you can really just run these all the way through. You can see, it does various outputs, goes through everything. And what we end up getting at the end are a nice little side-by-side comparison of all of the models. And then you can see that there is some variation in some of these because the way Molasses does its cellular automata, you can see that it's a little bit more kind of chaotic in the center and really only thins around the edges, whereas IMEX, because it has the kind of layered rheology programmed into it, has that more gradual thickness fall off. Lava 2D just seems to have some quirks with how it implements everything with the smaller scales. So we actually had to write some custom code for that. But though we do kind of get the fall off in Mr. Lavaloba or Floy, which had used the same kind of lobe-based comparison, you see that there's a bit of chaos around the edges as well, because of how those lobes sometimes fragment and add, if you look, just like some odd little extra edges or like, and then we, going on, we are trying to match up against the analytical. It might be a little hard to see here, but the black is derived from the analytical equation and is this curve around here. There's some quirks you can see, like IMEX, just because of how it starts the flux coming out of the point source. It does start at a non-zero value, but in the end, you can see it does very closely follow the analytical. And then this is also, still in progress, but this is let's see, the temperature profiles that we're working on, working through. And a lot of this is based on, I think, the Dietrich paper from 2017. And then we basically just do that 2 more times. With the inclined plane, we also allow you to change the angle. So, it allows computation of like internal friction effects. But similarly, we go on, we run all of these, and then you do see some unique effects here, especially with Mr. Lavaloba. Because of, again, because of the lobes, it doesn't quite close up into that elliptical shape because there's not that internal like stress holding it in that shape. So we can see this kind of fan out instead. And similarly, we try to run or give a trend for the downslope extent that was calculated. And then we also have that finally for a split flow. These notebooks there's actually much cleaner versions of these notebooks in when you run the command. Right now, we just, these are kind of these are just the versions that have all the outputs at which I'm using to kind of calculate everything in the paper. But long story short, this is for the split flow, which we're also still working on, and hitting an obstacle and how that affects the flow. And then I don't think I've mentioned, so we also have a benchmark physical, which is, in this case, users can basically pick any any like normal or any existing eruption. In this case, we're using I think the 2022 Iceland eruption. But if I let's see if I go through all this, yeah. So this one still definitely needs some work. I haven't touched this in a while, but uh, you can compare against that. And what we also have is all of our remote sensing code, which allows us to do things like, let's see, let that load for a second. Right. So yeah, this is us actually pulling out the disturbance profile of the Iceland eruption from remote sensing. Uh, the one we have most fully implemented is the one for the 2022 Mauna Loa eruption, but in theory, uh, you can apply that here or on any of our or on any eruption that has been in the past decade or so, because all of those have usually some type of profile, either from disturbance, which with Sentinel or Opera through the Opera pipeline, or through VIRS or FIRMS, which is like fires and thermal disruptions. But that's kind of our total suite, and the goal for this in the long term is that it's as modular as possible. So for any of these, like the split flow, like the inclined flow, um, you can change the angle, you can change the slope, and you can just everything is more or less pre-formatted for the user, so they don't have to worry about the minutia, and then they can, I actually have this paper up for reference. They can functionally get these results themselves, because a lot of these papers, though useful for quantifying the models and comparing them against an actual flow or actual physics, uh, don't often give the input files or give the process for how they actually uh, set this out. So what we're able to do here is give users a nice kind of tied up box and say you can run this as many times as you want, and you can vary the parameters, and it allows a lot more variation, a lot of testing. The one thing I'll say as kind of a caveat is that uh, we're using kind of a suite of tools that are more modern, but these also span a huge range. In the initial paper here, Flow 3D, VolcFlow, ComSol, OpenFOAM, all of those are physics informed. Molasses is the only one that has more of a stochastic process. But here we run everything from like an updated version of Molasses to Mr. Lavaloba, which goes through lobes, and then two models with slightly different depth average, less stratified, thermal. I'm trying to figure out the best way to put it, but like thermal approaches. So that's why we get a bit more variation here, and this is less of a reflection on the models as a whole, but more showing that there is variation, different approaches. Something like Molasses can take a couple of seconds at most, whereas something like IMAX may take a couple of hours. But all in all, it's reproducible, it's quick to run, and that is our goal in the long term for this code and or this kind of suite of notebooks. And then we already have something rudimentary, like a beta or an alpha for PDCs, and then we're also working with some researchers on making one for like gas content and mainly sulfur, but we're trying to work with all of the geochemists. I think that's all I have. At some point I can start going through BAM. Or if Sylvan, you want to take a like take a moment to talk through it briefly,
Yeah,
but I can also give some background.
yeah, I can introduce BAM a little bit, and then you can show the notebook. Just wanted to say, you've seen here briefly how, having Jupyter notebooks is actually super important because you can actually run several models, you know, 3, 4, 5 models in the same notebook. You can actually, put the input parameters there and then having the outputs all in the same notebook. So you can also do that comparison of outputs all in the same notebook. And the other thing that Sam briefly showed you is that you can also, even if you want to try to get the ground truth data to compare your models against, do some validation, you can also do that with, it's still a work in progress, but you will be able to do that very soon with downloading some remote sensing data that's going to allow you to look at the footprint of a new lava flow, for example, or a new parasitic density current that just happened at a volcano. Download that satellite image and then run some of these models and compare directly the output of this model to the new lava flow, the new eruption that just happened. So it's fully unique to have all of these in the same location, all open source for actually people to use and compare. So yeah, let me
All right.
quickly.
Do you have slides for this, or do you want me to just keep this up?
Yeah, I have some slides for this.
Okay.
Let me share my screen. So very quickly, just wanted to introduce a new code that we've been working on with my PhD student, Franco Garin. The paper is accepted almost in Bulletin of Volcanology, so it should come out in a couple of weeks. But it's basically an open source Python-based statistical tool for assessing the performance of numerical models in volcanology. So we mainly develop it for volcanic mass flows, but you can also use it for like plume models or even tephra modeling. The only thing you need is actually a raster, right? So you need uh, uh, an image that is georeference. That is, it's better that if it's georeference. There's some way to actually use non-georeference image as well, but it's better than if it's georeference. That comes as a raster where it can be, for example, the footprint of a flow that you can directly use as an input here. That's going to be your independent raster, and then you're going to have another raster that is the same size and same pixel dimension as your independent raster, and that dependent raster can be outputs of flow depths, for example, from a mass flow, or any kind of XYZ data georeference coming from a model. Okay. Then you're gonna take these couple of raster files and you're gonna run them through BAM with different modules. One of them is gonna assess the length, the runout length. So it's mostly looking at the runout of the footprint of a flow, for example. And it's going to compute some metrics for that. And then the other thing that BAM is going to do is going to run them through a confusion matrix where you're going to be able to get what we call similarity metrics, which look at, the best fit between the model and your independent raster in terms of spreading and runout. So really looking at the shape of your output, for example, flow depths or deposits compared to the real event. And it's going to do that by doing some traditional metrics and also some function transform metrics, looking at the false positive and false negative with some gradient going away from the footprint. I'm going to show you that. So the output that you get are some raster files, some figures, and some tables of results from these metrics, both the length metrics and the similarity metrics. All right, so we're using, like I was mentioning, we're using relationship between the area of the dependent raster and the independent raster. So we look at the match between the two areas, right? And so that's how the confusion matrix is based on what we call false positive, which are area where the model is going to go further than the real event, and false negative are going to be the inverse, where the model is actually missing some parts of the real event. And based on that, you can compute some metrics like this one here. One is called the Jacquard coefficient. This one is called the Dye-Sorensen coefficient. One is called the precision, and the other one the sensitivity, which either are using the false positive and false negative in blue and red here, or they're using only the false positive or only the false negative. The example we're going to show you here is based on the 2006 block and ash flows at Merapi volcano in Indonesia that I mapped during my PhD. So we have that map here in green of the deposit taken just a few weeks after the main event in June 2006, and we're running two models, Titan 2D and VoltFlow. So first, what the code is going to do is going to compute the different lengths based on some different approaches. So there's three main approaches that you can use in BAM. One is called the Euclidean distance. That is just a straight line between the first point in your area, in your footprint, and the most distal point in your footprint. The other one is called the manual length, where you're going to follow the main path of the flow. You can do that manually using an interactive window. And one is called the skeleton aggregate length, which is going to be computed to show you the main path of the flow, but also all the tributaries where the flow were able to leave the main channel, and spread laterally. In addition to that, it's going to compute the true positive, the false positive, and the false negative for your each of your models. So this is for VoltFlow here, and this is for Titan 2D at the bottom. And as you can see, it's going to highlight only the area that are, so for false positive that are going too far away from the main footprint for the real footprint, or areas where the flow is actually missing some area of the real event. Based on that, it's going to go a little bit further and say, okay, it doesn't only matter that the model is actually producing false positive or false negative. It's all false negative. It also matters how far away these discrepancies are from the footprint of the real event. So for that, we're also computing here what we call function transform, false positive and false negative, where we're gonna introduce an amplification factor for the false positive and a decay factor for the false negative. That, as you can see here from this heat map, are going to vary based on the distance away from the polygon, from your footprint of the real event. And so from that, we can actually get, so we're going to apply that factor from 1 to 2, either this amplification diffusion here or the decay diffusion for the false negative. And we're going to apply that to the footprint to have some new numbers associated with the false negative and the false positive. And based on that, we're going to produce the final maps, which are here displayed for VoltFlow and Titan 2D. The other thing I didn't mention that, but the other thing you can change is the minimum thickness of your footprint. So as you know, some models tend to spread a very thin flow away from the main flow. So if you want to avoid having that thin flow spreading, you can actually put a minimum thickness threshold. For example, here 1 centimeter. That's what we used. But you can use more or less than that based on what you're modeling, if it's a lava flow or a PDC or debris flow. And you can see the difference here between the using no minimum thickness threshold and using a 1 centimeter thickness threshold. So this is for VOGFlow and Titan 2D. So the gray area are the true positive. So the area where the real event and the model output are matching perfectly. Then the purple to yellow tones are showing you the false positive, and then the blue to green tones are showing you the false negative for each of the model. So you can see, for example, just looking at these figures, you don't have to look at the numbers here on the right side, but just looking at these figures, you can see, for example, that VOGFlow contain a lot of false negative, where it's missing to propagate where the real flow did, rather than Titan 2D is producing more false positive, which means that it's going to spread a little bit too much, right, compared to the real event. So in the end, the code is going to give you all this as a quantitative way, as this table here. So for each of the metrics you're looking, so the two length metrics and then the four similarity metrics, you can actually get some percentage here, for example, of match. For the Jacquard, for example, you can see we are just a little bit below 50% of match. The Dice Sorensen, because it's using the true positive twice, is going to put more weight on the true positive, so it's going to be a little bit less impactful on your model. And then here, the precision and sensitivity, you can see these numbers in red are just showing you where the models fail to reproduce the actual event. So for Titan 2D is going to be the precision is going to be pretty low because it's only taking into account the false negative, and then for VOGFlow is going to be the inverse. So you can see briefly here how the kind of quantification you're getting based on single events. So the goal would be to do that for multiple events and to integrate that into the benchmarking workflows that Sam just shared with you. So sorry, we're about the end, yeah, but maybe Sam, if you can show quickly the notebook.
I could show it, but you also basically showed everything that they would have seen in the notebook as well.
Yeah.
What I'll say is that I don't know exactly what the timing is, but I'd say in a month's time or so. We don't have a final version on Victor yet, but in a month's time or so, we should have a nicely packaged version of BAM on Victor for anyone to use. So we're just kind of working out the final tweaks. So we'll probably have that in our newsletter. So yeah, keep tuned for that. Yeah, I think that's all. I mean, if you want me to show it, I can, but it's more or less the it would have the same figures as you showed, and you did a very comprehensive job of explaining the process.
Okay. Yeah, I got a question about the minimum thickness. So it's basically the minimum thickness you want to use to compare the footprint. So for example, some models are going to give you some flow that are like 1 millimeter thick, and they're going to spread, quite laterally away from the footprint. So you may want to cut that model output, right, that model footprint to a particular value, basically saying, so for example, if I use block and hash flow, and I would say like anything that is less than 10 centimeter in a block and hash flow is not really representative of the real process, right? So I'm going to cut that footprint at 10 centimeter. But you're free to use the value that you want, and just be careful that the higher that value, the more you're going to cut the spreading of your footprint. So make sure you don't use values that are too high. And it's mainly based on the type of flow that you wanna model. So you may not want to use the same value if you have a lava flow, if you have a pyroklastic flow, or if you have a debris flow, for example. All right. I think it's time. Is there other questions?
I might hop to office hours in a moment, just in case anyone
Okay.
wants to go
Yeah,
into that.
yeah. So deposit thickness, yeah. So it's always a question of like, what are you modeling, right? So, is it the deposit or the flow outline? And that's kind of tricky, right? I would say use the deposit as much as you can, unless your model is not able to reproduce the deposit. Then in that case, you can use the flow outline. All right. Thanks so much, guys, for joining. And if you have any questions, put it on the Slack channel, and then we can answer it for you. And have a good weekend, and see you next week.